Okay, pre-cal, we're on to 1-3, continuity and behavior and limits. So we did some work with this on Khan Academy the last few days, and this is the first thing that you're going to get to in pre-cal, or sorry, in calculus next year. One of the first things you talk about is limits. So we really wanted to get a hold of that. So we did some Khan Academy work. Now we're going to kind of do it out of the textbook here. So continuity and behavior and limits. Let's start with some definitions. A lot to get through today. So let's get through it. All right, so continuous function. The graph of a continuous function has no breaks, holes, or gaps. So you've seen some of those where there's a hole in it, where it doesn't, a value's doesn't exist at that point in the graph, or maybe there's breaks in there. We've seen all sorts of types of those graphs or gaps. Basically, you can trace the graph without lifting your pencil. Okay, and then a limit. We talk about a limit. The limit is basically the concept of approaching a value without necessarily ever reaching it is called a limit. So you keep getting closer and closer and closer to a certain value, but you don't ever really get there. Then we call that a limit. Okay, moving on. As we talk about the limits here, you can kind of look and read this over on your own. Pause it here. But basically, we're looking at if the value of f of x of that function, if it approaches a unique value from each side, and in this case, in the picture here, as f of x, as x approaches c, we get closer and closer to the certain value. That's what we're kind of looking at. So again, when we look at this graph from each direction, right, we look like f of x, as x is going closer and closer to c here, what's happening to the function? It's getting closer and closer to this point right here. Even if you go the other direction going this way, it's getting closer and closer if you're coming on x this way. And that's kind of the idea. It might not ever reach it. You can get closer and closer and closer without actually touching it. That would be the limit. And here's your symbols. You've got the limit, in this case, of f of x equals L. We would read that as the limit of f of x as x approaches c is L. You got limit here, and f of x equals L. And you've got this little x with the arrow, x approaches c, is what we're talking about there. Okay? Easier when we get actual values or infinity in there, and we'll talk about that as we go. All right, discontinuous functions. So these are the ones we talked about that have gaps. So these are not continuous. It's the opposite of continuous functions. They actually have some breaks or holes or gaps or some other reason why they're not continuous. You can't trace this with a pencil. Okay, and then we have different types of discontinuity. Okay, so these are the most common types of discontinuity. You've got infinite, you've got jump discontinuity, and removable discontinuity. So take a look at the example for infinite over here. Your example. X equals c is where they will never touch, right? So at x, you'll see the function value increases or decreases indefinitely as x approaches c from the left and right. So you can see as we get closer to c, this function, all of a sudden we go infinitely higher, and then from the other side we go infinitely lower, and they don't touch. That has what we call infinite discontinuity. Jump discontinuity, this is where there's a break in the graph. Okay, you can see right here, this graph would be in this direction, ends right here, but then we jump up here. We call that a jump discontinuity. And then removable is basically so removable discontinuity is, you've seen these before where the graph goes up and then there's the hole in it right here. It's the same function, and it continues on after that hole, just is removable. We can basically remove that point. Okay, so continuing on. Let's look at the next page here. Okay, so continuity is a function, is continuous, okay, is continuous at x equals c if it satisfies the following conditions. Okay, so there's a few conditions it has to have for it to be continuous. So number one, we look at it. function is continuous at x equals c if it follows the following conditions. So let's write those in. Number one, f of x is defined at c. Okay, so again, we're talking x equals c here. That's why we're using those terms. So it's defined at c, which basically means that f of x exists. We have a point at f of x. There's no hole, there's no gap. We actually have a value at c. Okay. The second thing is if we look at f of x, let's try to get a little bit lighter writing here. Good. Let's hope that works. Okay. No, it didn't work. Okay. F of x approaches the same value from either side. So this is where we talk about limits. So it approaches the same value from either side, meaning from the right or the left. Right over the left, which basically means what we're talking about there is that your limit exists. So you have a limit of f of x exists. As we talked about x approaches c. That exists. Okay, so you kind of have an actual value, and the second thing is you have a limit of f of x. And so then we also talk about the third thing being that third thing we have is that basically the value that f of x approaches so the value that f of x approaches, basically the second step, right, is f of c. So basically, these are basically saying these two are the same. They're the same, then it's continuity. So again, basically saying here that the limit as x approaches c is equal to f of c. All that's really saying is that if we have a point that exists, we have a limit that exists, and that limit is that point, then we have continuity. That means there will be no holes, breaks, or gaps in our graph. All right, so let's move on. Let's go practice. Determine whether the function is continuous at a given x value, and then you can justify using the continuity test. If it's not, if it's discontinuous, identify the type. Is it an infinite? Is it jump? Is it remove? Okay, so we've got a lot of testing to do here. So the first thing we're going to do is just remember this is a square. I think it's like that on yours. 2x squared minus 3x minus 1 is continuous at x equals 2. So our first question here has got to be, number one, does f of 2 exist? If we're looking at x equals 2. So our first question we're asking here, does f of 2 exist? Okay, so we basically are going to plug in 2 into this function. So we're going to say, all right, 2 and see if we get an answer, right? I guess you could do this with a calculator as well. All right. So when we do this, we can just kind of do the math. I'll just kind of keep going here left to right. So 2 squared is 4. So we have 2 times 4. And we've got negative 3 times 6. We have a minus 6. And we've got that minus 1. Well, all told, that's going to give us 8 minus 6 minus 1. So we're going to have a 1. So, yes, check. It does exist. So, yes, we can put a yes in here and say, yep, it exists. So, number 2. Okay. Does the limit, go back to purple, does the limit as x approaches 2, now we actually have a value, right? As x approaches 2, does the limit of x, f of x, exist? So this is our test, remember? So from above, you got those 3 criteria we had to fit. Now, this is where it gets a little kind of bummerish, where you've got to actually do some work with a table. If you have a calculator handy, it's great. Okay, so let's kind of put a little table in here. Actually, not a little table. It's going to be a large table. Okay, and here you're going to have x, and then down below you're going to have f of x. We're just kind of getting a table of values. So it kind of helps to have a bunch of values and a bunch of room here. So it does help to have a calculator. Okay, so we also know that we're approaching 2, right? That's the thing. So we're going to kind of put 2 in the center here as x approaches 2. So I'm going to put it right in the middle, 2.0, and then I'm going to make that its own column. So we should have kind of blank there. We want to get some values that are approaching it as we go. So kind of want to go 3 values on each side. So I'm just going to kind of make 3 more columns here and 3 on this side here. Okay, so now I can plug in some values. So as we're approaching it from the left, right, from before 2, so less than 2. Let's say if we just went like 1/10 away, we put 1.9 in there. Okay, so we're just going to give our values. We're going to use 1.9, but as we get closer, you know, if we go another 1/10, we're at 2, but we can get smaller and not quite be at 2. So if we went to like 1.99, that would be, you know, closer yet to 2, but not quite touching it. And then finally, you could go 1.999. Okay, so those values, as we can see, we are approaching. So again, another way to look at it is if we say as x approaches, you know, 2 from the left here, we also are going to have it from the right. So we're going to have x approaches 2 from the right going this way. Okay, so that means that the values on the other side are going to kind of be like this. So you're going to have what, 2.1 over here if we go 1/10. Then if we go 100, 2.01 as we get closer, and then here 2.001. So looking at it from a table. So now we can plug in all of these values, all of these into the function above, into this function here. So we can do that. That's going to be calculator work. I'll do the math for you today for this particular problem. So you're going to end up with 0.52 for that one. I'm sorry. Yeah, you know, you're right. Good. 0.95. Almost looked at a different example. And then 0.995. So we're getting closer. And then on this side, we're getting closer to a certain value, right? And over here, you're looking at 1.52, I think. Yep. And then 1.05 would be here. And then as we get even closer, it'd be 1.005. So we can see as they're approaching a certain value. They're getting close to something from each direction. And what number are they getting close to? Well, we're almost to 1, and we're almost to 1. And they're getting closer to 1. I'm not going to put it in the table, but we're getting closer to it, right? So we're getting closer to f of x being 1. So I would say because that is a continuous value, we're getting really close to that value. That would exist as our limit. Our limit would actually be that 1. Okay, so that does exist. So we can check that box as well. Check. That exists. So now for it to be continuous, those two things have to be the same, right? And basically what we're looking at now is we're going to say the limit as x approaches 2 of f of x as x approaches 2 is equal to step 1, f of 2. They were both 1, right? We had our 1 over here that we got. We had our 1 right here that we got. So they were both equal to 1. So that checks that box as well. So we know that it is continuous. All right. So that is how we do it. Yes, there's 3 steps to it. You know, there's a lot of easy calculations to go when we get it from the table. All right, let's check this next one. Okay, here we go. All right, so this one, we've got a little bit different situation because it's a piecewise function here. So we can kind of look at it here and say, all right, let's go with step 1, right? Does f of -3, get rid of that, Does f of negative 3 exist? Okay, that's the big question. Okay, so if I plug in a negative 3, yes, I end up getting 5, right? Right, because I can plug it in here. 2 minus 3, 2 minus a negative 3 would be give me 5 after making it positive. Okay, so we know that exists, so we can check that box. Yep, check. Got it. Good. All right. Number 2 on the list here says, do we have a limit as x approaches negative 3? The limit of f of x, does that exist? Okay. So now here's where we got to make our box. Okay. And again, I'll kind of speed through this one for you just so we can check it out and take a look. So again, I've got x, I've got y, or I guess I should say f of x, right? X and f of x here. Okay, and then separate those in my table. And remember, I'm trying to find this negative 3, so that's going to kind of be in the center. And then I want 3 values to each side, so as close as we can get. So if I break these into columns again. All right, so let's start at 10th away and then go basically thinking 10th, 100th, thousandths. Okay, so as we're approaching, x approaches negative 3 from the left. We do that, and then we'll have x approaching negative 3 from the right. Okay, so we start in our farthest away as a 10th, negative 3.1. Then we go negative 3.01 and negative 3.001. So we kind of go 10th, 100th, thousandth. Same thing over here. You know, if negative 2.9 is a 10th away, then negative 2.99 is a 100th away, and negative 2.999 would be a 1,000th away. And now we can plug those values in. Again, I'll save you the time in doing that, but when we do that, you'll notice we end up with a little bit different value. We've got a 5.1, 5.01, and 5.001. So it looks like we're approaching 5, right? It looks like we're approaching 5. But on the other side, if we plug in those values, you're going to get 10.7, 10.97, and then, sorry, it should be negatives, right? Yeah, negative, and then negative 10.997. All right, so in this case, we are approaching from this way, we're approaching what appears to be negative 11. Okay, well, that's no good because this is not the same. So they're not approaching the same value. So we know that while it has a limit, it's not the same value. So we know that this is not continuous. So we can say no. And then basically, what type of function would this be? So what we'd see if we graph this thing is that you'd have a point at negative 3, and it would jump from like 5 up to or down to negative 11 in your graph. So this would be one of those jumping points where we have jump discontinuity, discontinuity. Because we're approaching a value, we're approaching something that's not infinitely, and it's not approaching the same value, so we know it jumps here, so we jump discontinuity. All right, little bit left. Let's talk about end behavior. All right, end behavior. This describes how the function behaves at either end of the graph, or basically saying what happens to the value of x, the value of f of x as x increases or decreases without bound. Okay, so basically as we're getting closer to infinity or negative infinity. So you can use that concept of a limit to kind of describe what's happening at the end behavior. So we're looking at, as you get closer to the end, what is happening there. All right, so left end behavior, that's the left side. So that's when x becomes more and more negative. So a lot of times we write that as x approaches negative infinity because you're getting more and more negative on the left side. So farther and farther negative you get approaching infinity. And then right end behavior, that'd be the right side. Remember, right is positive for x, left is negative. So this would be more like as x approaches positive infinity, right? And your f of x values, your y values, right? They might approach infinity. They might approach negative infinity. So we could say as x approaches infinity, f of x approaches negative infinity. That could be the case. It might, your f of x values might approach infinity, or they might also have a specific value that they approach. As x gets bigger and bigger, f of x approaches, say, 6, for example. It could be a specific value, okay? So this graph here kind of shows left-hand behavior, right-hand behavior, things like that. Again, rewind, pause as you need to. I just want to kind of get done here so it's not such a large video for you, so you can always rewind, do what you need to do. So our left-hand behavior, right? So if we're looking at that left-hand side, we're thinking limit of f of x as x approaches negative infinity, right? We're talking about the left-hand side here, right over here, okay? And then the right-hand side would be the limit of f of x as x approaches infinity, right? That would be the right-hand side because x is getting more and more positive. So that's kind of why we use the concept of limits. All right, so looking at the left-hand side, what's happening to x? X is getting farther and farther this way. So x is actually approaching that negative infinity over here. Okay, negative infinity. Okay, and then what's happening to y though? Y is actually getting larger and larger. So f of x is actually approaching infinity. So our limit here, we could say equals infinity because f of x is actually getting larger here. On the right-hand side, right, you've got x is getting farther and farther to the right. So x is approaching infinity here. It's like we have up here. But what's happening to y? Y is actually going down. It's getting smaller and smaller. So as it continues to go, y is going to be equal to negative infinity, or f of x is going to be equal to negative infinity. So that would be kind of our x and y axis. Again, just remember, the farther we go this way, we're talking about x going closer to negative infinity. Farther we go this way, we're talking about x getting closer to infinity. Same with the y-axis. If we're going up, we're thinking f of x is your y values, right? That's approaching infinity as it goes up. As it goes down, we have f of x approaching negative infinity as it goes that way. Okay, so a lot of times that's what we get when we talk about n behavior. So let's do one practice problem to talk about it here. Let's look at this graph here, x cubed minus x squared minus 4x plus 4, and talk about n behavior. So we talk about the left end first. Let's talk about the left end. As x goes the farther end this way, as x keeps going left, what's happening to the n behavior? It's going down. So as x is approaching negative infinity, yikes, then y is also approaching negative infinity here. Okay. So we could say as x, as we write that as a statement, as x approaches negative infinity, f of x approaches negative infinity. So that's the left-hand side. Now we need like an and here because we're going to do the other side as well. If we look at the right side, the further and further we're going to the right here with this graph, the further and further up we're going. So we're getting closer and closer. So basically as x approaches positive infinity, f of x, I should say y down here, y is approaching positive infinity. So we could also say now on the right end behavior, as x approaches infinity, f of x approaches also positive infinity. And that would be your end behavior. I know we did a little work on that in our review in the beginning of the year, our function review. Okay, that is it on limits, continuity, end behavior, things like that. So, wow, long one, 24, but there was a lot to get to. So, go back, write anything down you need, bring your questions to class. See you next time.